Um,
This meeting is being recorded.
All right. Hello, everyone. Welcome in. Thank you for coming to our AstroCheminar online seminar series for April 2023. My name is Kyle Crabtree. I'm chair of the subdivision. I'm joined by my fellow officers, past chair Heather Abbott-Lyon, chair-elect Chris Bennett, and vice chair Michelle Nuevo, along with our secretary, David Woon. We're happy that you're here today. We've got two exciting talks for you today, but before we get right into those, I do have a couple of announcements. First, we're really excited to announce the winner of the 2023 ACS Astrochemistry Dissertation Award. And this year, that award has been granted to Katarina Jochum. Dr. Jochum worked with Susanna Whittakis-Weaver at Emory University and then later University of Wisconsin-Madison for her PhD studies, that she's currently a postdoctoral fellow. So congratulations to Dr. Jochum, and we look forward to seeing nominations for other outstanding candidates for the ACS Astrochemistry Dissertation Award next year. The deadline for nominations will be in January of 2024. So if you have any candidates who are either going to complete their PhD this year or have completed their PhD in the last year or two, please do consider nominating them for that award. There's additional information about that on our website. The other announcement that I want to have is that this is currently scheduled to be our final AstroCheminar of this spring semester. It's now 2023. We started this seminar series in the fall of 2020. In response to the COVID pandemic. But now, being toward the end of the 2022-2023 academic year, a lot of conferences have resumed. There's a lot of travel happening, and so we've been thinking about whether we should continue offering these AstroCheminars on a monthly basis, or whether it would be time to conclude the series or continue it at perhaps less regular intervals. We would be happy to hear your feedback from the community on what you think about this seminar series going forward. If you've really benefited from it and think that it should be something we continue regularly, we'd love to hear from you. If you think a less frequent schedule would be appropriate, that would be useful information as well. Or if you have other ideas about ways that we could use virtual tools to keep connecting with the astrochemistry community, please do share that feedback with us as well. We would love to hear from you. So with that, those are the announcements that I have today. Let's get into our first talk. And our first speaker today is Dr. Julianna Palotás. So Dr. Palotás obtained her bachelor's and master's degrees in physics in Budapest, Hungary. After her studies there, she moved to the Netherlands and worked in the group of Professor Jas Omens at Felix Laboratory under the Horizons 2020 Marie Sklodowska-Curie IT and Europa project, and part of the Dutch Astrochemistry Network too. Currently, she's a postdoctoral researcher in Professor Leah Dodson's group at the University of Maryland here in the United States. So Dr. Palotás, you can go ahead and start sharing your screen, and I look forward to your talk. In the meantime, if anyone has questions for our speaker, you can feel free to open up that Q&A tab at the bottom of your screen and post your questions during the talk. You don't have to wait for the end, and it looks like we're all ready to go, so I'll hand it over.
Okay. Thank you very much. Welcome, everyone. Thank you for this opportunity to present this work on this webinar series. In the next 15 minutes, I'm going to talk about my PhD work that I was researching in the Netherlands, as it was already mentioned, with Professor Jas Omens. The main focus of this PhD project was to study the vibrational spectra of different ionized fullerene derivatives. Yes, okay, it's working. So fullerenes, particularly C60 and C70, were discovered in 1985 accidentally in an experiment that was aimed to understand the carbon chemistry in circumstellar environments. That discovery resulted in a Nobel Prize for curl, croto, and smalley. And it also opened up many research fields around fullerenes, obviously. So during that time, it was already proposed that these molecules, C60 and C70, can be present in the interstellar environment, and they can be very interesting for the astrophysical communities. However, with the actual detection, we had to wait till 2010 when an emission spectrum from a young planetary nebula was overlaid with the vibrational spectra of neutral C60 and C70, as you can see here on this figure. And with this detection, C60 and C70 became the largest molecule found in space. We are not only interested in the neutral molecules, C60 and C70, but we are also very curious about other derivatives of this molecule. One of his early papers, Sir Harry Croteau, that you can see here on this figure, on this picture, proposed that the protonated C60 is likely to be the most abundant fullerene analog. So we are also interested in ionized form of these molecules. However, no one really measured these protonated ions before because of the challenges of these experiments. What we did at the Felix laboratory in the Netherlands, we used action spectroscopy technique. So we combined mass spectrometry with ion spectroscopy to measure the vibrational spectrum of these protonated ions. So here, with a mass spectrometer, we can select and isolate a certain molecule, certain ion that we are interested in. And we irradiate these molecules, these ions, with very tunable and powerful laser light. And if the frequency of the laser is on resonance with the frequency of the ion, we will see fragmentation. If we have a highly tunable laser source, we can do this measurement, the fragmentation, at many, many wavelengths, and we can record vibrational spectrum, the one that you can see on the right figure here. For the experiment, we used a commercially available Bruker mass spectrometer that was modified to have access to the ions for the laser light here. We used Felix, the free electron laser that's widely tunable in the fingerprint region, the one that we are mainly interested in for this vibrational spectrum. To produce these ions, we use atmospheric pressure chemical ionization source. That's a really good tool to study gas phase gas phase apolar molecules, because it uses high temperature and high voltage to create a reaction plasma that can protonate and also create some radical cations of the certain molecule we are interested in the gas phase. So as I said before, it's what our source is producing is a superposition of radical cations and protonated species. So a normal mass spectrum that we will see from these fullerenes will be something like this here in the top figure, where you can see that the 721 mass here corresponds to the protonated C60, but we also see traces of radical cations. So with our experimental setup, we isolate this peak and we irradiate it with the laser light. Then we will see a new fragment, the 720, so basically one hydrogen loss appearing. What interesting is that with this technique, with this laser, we cannot break the carbon cage. So we won't see fragmentation, we don't see many channels of fragmentation, only one. And that will result in a very clean and a very good quality spectrum. C60 is a very symmetrical molecule. It belongs to the icosahedral symmetry group. However, if we attach one proton to the carbon cage, we basically get rid of all the symmetries that the molecule had before. So only one symmetry will stay, and this is a mirror plane that goes through the proton. And the new molecule, the protonated C60, will belong to the CS symmetry group. Due to the high symmetry of the neutral molecule, the vibrational spectrum of the fullerene, the C60, is very sparse. We have only 4 modes, only 4 vibrational modes here. However, if we get rid of all the symmetries, we expect a very rich vibrational spectrum. And this is what we saw in our experiment compared to the very empty neutral molecules vibrational spectrum. We get a very rich spectrum here. And I would like to point out that here we have like very large peak in the shorter wavelength region. And if we go to the longer wavelength part, then it's like smaller peak appearing. We did the same measurement with C70. In the middle figure shows the middle spectrum shows the protonated C70. If you compare this spectrum to the neutral C70, you can see the difference again. So very similar, like a symmetry breaking effect happening here as well. And if we compare it to if we compare the protonated C70 to the protonated C60 spectrum, we will see some very lots of similarities here. Again, the large peaks in this part and smaller peaks appearing the other part of the spectrum. We have a different problem with this molecule, however, because C70 is not that symmetrical than the C60. It has 5 different configurations for protonation, and we would like to know that which one is the one that we are actually measuring, which one is the one that appears in our experimental setup. So for that, we used DFT calculation to determine the right protonation side. And the theoretical work, the DFT calculation here is the spectral with blue lines. It shows the 5 different configurations compared to the experimental spectrum. That's the black line here in every figure. If we do this comparison, we will see that we can actually tell that which isomer formed in our experiment, and this is the lowest energy isomer in our case. Not only the protonated species, but other low symmetry fullerene derivatives can be very interesting for the astrophysical community. In this early paper, Croteau also mentioned the C60 with oxygen on the carbon cage. So our natural next move was to study that species. In the APCI source, we could also see 2 peaks, one at 736 and another one at 737 that correspond to the C60O, and the other one to the C60OH ions. If we focus on the oxidized C60, we have 2 different isomers again, as we had with, similarly as we had with the protonated C70. There is one isomer that where the oxygen bridges to hexagon. This is the one on the right. And if we have another configuration, then it bridges between a hexagon and a pentagon. And we do again quantum chemical calculation to determine which one is the right structure. In this case, interestingly, these isomers are very close together energetically. So it's not that obvious from just reading the energy of the different configuration, that which one is the one that will be formed in our experiment. So we definitely need experimental result next to the DFT calculation to determine the right structure. And in our experiment, we are forming this 5-6 configuration that you can see here in the bottom figure. That's the one that's matching the experimental spectrum. Again, the colored lines are the theoretical spectrum. And I would like to point out again that we have a very similar spectrum to the one that we've seen before with the protein that's C60 and C70. When we did the experiment on C60OH+, so adding one OH group to the carbon cage, this is the spectrum that we could obtain. That again, a very similar vibrational spectrum to the protonated species. In this case, we could also measure with an OPO laser the OH stretching that you can see here on the very right side. So what we found, we compared these spectra, these vibrational spectra, to again, a young planetary nebula that we know that very rich, very fully rich. We know this because it has very distant peaks. The one that shows here with red, this 4 peak, that belongs to the neutral C60 vibrational modes. So in this fully rich planetary nebula, and there is a very interesting feature between 6 and 9 micrometer. This is a plateau that we couldn't really explain before. And our hypothesis is that it's nicely fitting into this trend that we noticed with the ionized low symmetry fullerenes. Individually, they cannot really explain this envelope. However, maybe a mixture of this fullerene derivatives could explain this this part of the spectrum. And we are also interested in other species, not only the protonated and oxygenated species, but maybe other low symmetry fullerenes could contribute to this part of this astronomical spectrum. I would like to thank my supervisors from Felix, my former supervisors, Jos, Hill, and Jonathan, and the whole Felix staff, who did an amazing job with the free electron laser. And I would like to also mention my current group at the University of Maryland, and I would like to thank them for the support. Thank you.
Thank you. That was a very, very nice talk. We've got a question already for you in the Q&A section, so I'll read that one out to you. This is from an anonymous attendee. They say, "Very nice talk. Would you expect to learn anything interesting from studying the spectra of C60 with a deuterium in addition to the protonated form?"
I mean, like in a spectroscopic view, it will be like a very similar spectrum as we could like measure with a hydrogen. So like it's not like a huge difference, I would say. We did some like theoretical calculation on that, and it's actually a very, very similar vibrational spectrum to the one with the hydrogen atom. But maybe like in the mass spectrometer, that can be interesting to distinguish, for example, with the carbon-13 isotope, because obviously the mass will shift in that case. So that could be something interesting to see.
Okay, I was curious for the C70H+, where you had different configurations that were all fairly close in energy to one another. Did you explore the barrier between those different configurations? Like, what is the barrier to the proton migrating on the C70?
Oh, the migration. So if I go back, so actually if you look at this, like different energies of this 5 isomer, right? These two, so this D configuration, and I think this one is the B configuration here, they are very close with energy, but the others are very far. So like 20 kilojoule per mole difference, it's like really like a huge difference between the lowest energy configuration. So I would think that I didn't, so the short answer is I didn't calculate that, but I would think that the barrier would be something still very large here. It's interesting, it can be interesting to see the difference between these two because they are so close with energy.
Great. We have a question from Maria Merganj in the Q&A. She says, thank you for the talk. How stable are the oxidized fullerenes? What is the dissociation energy of the C60O?
I don't know this on the top of my head. I'm not sure about this. I'm sorry. It's so like what's interesting is that it's really easy to form these molecules. So like basically C60O just happens. Like I don't even have to really work hard on it to like be in this experiment, because in this reaction plasma it just forms from the oxygen that we have in the air. I would think that makes it as a very stable molecule. So
that sounds good. We have time for maybe one more question if anyone wants to get them into the chat, and while we wait for to see if anyone else wants to ask something, I would want to ask, can you say a word or two about what you're currently working on?
I'm sorry, that was for me?
Yes, that's for you.
Oh, yes. So at the University of Maryland, we are working on ions with like metal ions and how they interact with like smaller neutral molecules. We are building a mass spectrometer right now in the Dodson group and study the kinetic rates of the formation of these molecules.
All right, one last question has come in for you, and so this will be the last one to wrap up with. If people do have other questions, you can continue to submit them in the Q&A or in the chat, and Dr. Palotás can type the answers during our next talk. But this last question is from Ralph Kaiser, asked, have you checked out any fullerenes with an atom or ion inside the fullerene, so any of the endohedral fullerenes?
I think it's a really good point. Like I did a theoretical calculation on that. So we were like trying to understand that more. However, in this setup, we are very sure that we are not making those molecules. And we didn't go into that direction because that would require like, like another collaboration with a chemist to make those molecules. So like with this source, we cannot produce endohedral fullerenes. And again, with theoretical calculation, we can really confirm that this is not what we made here. But it's definitely interesting, the endohedral.
Oh. All right, well, Dr. Palotás, thank you again for a very nice talk. We are going to go ahead and move on to our second speaker for today. And it's a pleasure for me to introduce Dr. Partha Bera. So Dr. Bera is a research scientist at the Bay Area Environmental Research Institute, and he works at the Space Science and Astrobiology Division of the NASA Ames Research Center. Before this, he was a postdoc fellow at NASA Ames with the NASA postdoctoral program. He received his PhD in quantum chemistry and electronic structure theory from the Center for Computational Quantum Chemistry at the University of Georgia. He received his bachelor's and master's degrees from the Presidency College and the University of Calcutta. His research investigates novel chemistry of the evolution of complex organic molecules towards becoming biogenic in astrophysical environments in the spectroscopy and atmospheric chemistry, gas phase molecules using the techniques of ab initio quantum chemistry. Dr. Bera is a member of the ACS and has served as an officer of our subdivision, the astrochemistry subdivision here, and he was one of the core architects of helping us get this AstroCheminar program off the ground. So it's a real pleasure to kind of bring things full circle and have him give a talk here at this at our AstroCheminar this month. So with that, I look forward to your talk, Dr. Bera.
Thank you, Kyle. Can you hear me?
Yes.
Okay, so I'll keep my camera on for some time and then I'll switch off just to save some bandwidth. Thank you very much for giving me the opportunity to talk here. I know when we had started this AstroCheminar series, and so it's a real pleasure to come back and give a talk here. So I'm going to talk about pure and nitrogen substituted cyclic aromatic hydrocarbon formation in the gas phase, and everything I'm going to talk about today is to do with the gas phase. So no ice, no surface, any type of reaction like that. If we can go to the next slide. Here's just a quick overview of what I'm going to talk about. I'm talking about bottom-up synthesis of organic molecules, and specifically what does it take to make some of these feasible. And in this talk, I'm going to break down the talk into two large segments. One, sort of fragments combining with each other. These are your HACA, PAC type of mechanisms. It may be radical molecule reaction. It may be ion molecule type of reaction where small molecules, small organics come together and react with each other to make slightly larger molecules, sometimes even small PAHs and nitrogen substituted PAHs. And the second part, I will talk about neutral clusters, sort of nucleation type neutral clusters coming together, and then either making a radical or ion to make reactions possible. And then I'll hopefully have time to take a few questions. So let's go to the next slide. I'm going to start by with this slide, starting from 2010 onwards, I would say. Dr. Doran Parker, Professor Ralph Kaiser started these experiments probably earlier too, I'm not aware, where they would investigate these HACA type mechanisms where acetylene will react with a radical, either a phenyl radical or a pyridyl radical to make bigger PAH type bicyclic, either pure or nitrogenated hydrocarbons. So if you put two acetylenes together with pyridyl, ortho or metapyridyl, you would get quinoline or isoquinoline. Only problem was that they could make these. Only problem was that it happened at a slightly elevated temperature of about 1500 Kelvin. And then they designed another experiment where they thought, well, if we put two instead of two acetylenes, if we put butadiene, which already has that carbon-carbon bond, so it's a 4-carbon starting material, along with the same radicals, can we make then quinoline? It will be dihydrogenated, but still it was doable. So they could produce that in the laboratory, and they could produce the pure hydrocarbon equivalent of that as well. And we did the theory, if you can go to the next slide, of that, and we looked at, so we'll start with this, this chart on the right, where we have a pyridyl radical with 1,3-butadiene, and it makes a small, quick sigma complex that goes through a transition state which is submerged. We spend quite a bit of energy into figuring out the barrier to this little transition. It turned out to be just below the separated reactants, and it goes to this this intermediate, which then unimolecularly decomposes into various products. Some of it linear branch or sort of a branched cyclic molecule, and others are more like a PAH type, nitrogenated PAH type, and that's the big revelation here, that we could then say that these reactions then happen at at very low temperature because it does not really require any barriers to cross, that is above the separated reactants. So we then took this surface and applied unimolecular RRKM theory and got the rate constants for these unimolecular decomposition, and then from that we figured out the branching ratios. And it turns out that dihydroquinoline is the most dominant product, basically 100% of the product in this case. So it was a nice investigation to figure out that these reactions can actually happen in cold temperature as low as 10 Kelvin. So with that, I would like to go to the next slide. We then thought maybe we can do another study, including this time vinyl acetylene instead of butadiene, which has two less, vinyl acetylene has two less hydrogens. So, and this is work that is incomplete, still undergoing. And so we could make the quinoline and isoquinoline, but the story is not complete, and it's not, doesn't look like it happens at below zero, sort of. It looks like there's some barrier to cross here, not exactly like zero barrier. So that's to do with radical molecule reactions. If we go to the next slide, we would see. I then started thinking about ion molecule reactions as well. Here, the simplest thought was to put acetylene with its ionized counterpart, acetylene ion, and try to see what we make. So we were trying to figure out the bonding pattern, the ion, the energy it requires to make, and what kind of bonds, what kind of structures it makes. So we put acetylene with acetylene cation, ethylene with ethylene cation, and the cross combination of the two, and see what we make. So if you go to the next slide, we see that that we actually make carbon-carbon bond formation is rather easy and does not require any going over any barrier. So a C2 type, a C2 symmetry linear chain forms first at 39.3 kcals per mole between acetylene and acetylene cation, which then goes through a bridged kind of structure to a boat structure, which you see on the top right corner. This boat is simply cyclobutadiene, but it has one electron missing, and therefore it puckers out of plane, and so it's called a boat, and it's pretty strong. It's strong, bound by 87 kcals per mole energy from the separated reactants, meaning acetylene and acetylene cation. If you look at ethylene and ethylene cation, that too is pretty strongly bound. That boat structure similar by 35 kcals, and the cross molecule is also bound by 55 or 56 kcals per mole. So carbon-carbon bond formation is easy, and cyclization is also rather easy. It does not require any barriers to cross, but it makes pretty stable, strong cyclic molecules. This was so. If we go to the next slide, our conclusion from this part of the work was that this electrostatic interaction between the ion and the neutral made covalent bond formation possible, and it made cyclic molecule formation possible as well upon encounter. And this barrierless cold condensation of molecules and ions was a viable mean for hydrocarbon formation, cyclic hydrocarbon formation. But as we will find out that later, that this growth potential is kind of limited, because it makes such strong cyclic molecule that it takes a lot of energy to break it open for further growth. And so any growth, if you put another acetylene with it, it doesn't really make benzene cation or phenyl cation with that cyclic 4-membered ring. It attaches to the side. So it is good that it makes cyclic molecule, but it's kind of bad because it's not very easily broken. So we had to think about other ways, look at other ways we could make cyclic molecules that are bigger, maybe 6-membered, and we looked at fragments. So if we go to the next slide now, around the same time, our colleagues in NASA Ames, Cesar Contreras, Farid Salama, were experimenting in their cosmic experiments in plasma, where they were using acetylene, ethylene, and sometimes aromatic molecules as feedstock gas, and then producing ions and fragments. So these on the left, you would say fragments that they were creating: carbon plus, CH plus, C2, C2H plus, and C2H2. All these fragments they were creating, and they're seeing products as well. They're seeing 4- and 6-membered, six carbon products with varying number of hydrogens. So 2, 3, 4, 5, 6 number of 5 hydrogens. And so this plot shows in an electron impact and in plasma experiments, they see up to 76, 77 mass shows phenylcation perhaps. And so we started thinking that what could be the asymptotes that produces these molecules, and what would be their structures. So if you go to the next slide now, we looked at these asymptotes C2H2 reacting with C2 plus to make C4H2 plus, and which then can react with either a C2 or C2H2 to make C6H2 plus or C6H4 plus. We then looked at C2H2 reacting with C2H plus. All these fragments are produced in the plasma, as you saw in the last slide, to make C4H3 plus, C6H3 plus, C6H5 plus, and so on. Of course, many other asymptotes are possible, including the ones where you have A plus B reacting to make C plus D type of reaction, which is the most important type of reaction. So we looked at all of these types of asymptotes. I'm going to share a couple of them in the next couple of slides. So next slide talks about acetylene reacting with C2H plus. And so you would see you make, without any barrier, you make the cyclic molecules, you make the linear molecules. They're connected with each other by some kind of internal rearrangement. And in this case, the linear molecule, linear carbon chain with 2 hydrogens in one side and 1 on the other, is the global minimum. So C4H3 plus has a linear structure, although C4H4 plus is cyclic, not the both one. That its global minimum is a 3-membered ring with 2 hydrogens on each side. But in any case, you make cyclic molecules as well as linear molecules. If we go to the next slide, that's another of these asymptotes where we took that C4H3 plus that we made with C2, just C2, and that produces C6H3 plus. That's the asymptote I'm showing here. There are other asymptotes in the paper as well, but this makes now cyclic as well as linear molecules, and the linear molecules are directly connected with the separated reactants or asymptotes, and it makes C6H3 plus. C6H3 plus is a particularly stable molecule because it has 2 types of aromaticity going on, sigma as well as pi aromaticity going on. It's a really stable molecule, and lots of papers are about it. And we make that using C4H3 plus and C2, and so cyclic molecule, including going up to 6-membered ring, is not difficult as long as you have the right ingredients and the right conditions available. And so that's for this asymptote. If you go a little bit farther, if we take next slide, these are experiments that showed that C4H2 plus, if you reacted with acetylene, can make C4H4 plus, as we showed in another paper. That actually C4H4 plus can cool very easily by expelling a proton or a hydrogen to make C6H3 plus, and this is sort of because C6H3 plus is so stable. Let's go to the next slide. Next slide talks about C4H3 plus reacting with acetylene, and now it makes C6H5 plus, which is a phenylcation. You already see that this field of low energy isomers are pretty busy, complicated. You have the semi cyclic molecules with side chains hanging out from the side. You have purely linear chains, branched chain molecules in the middle, and you have cyclic 6-membered and 5-membered rings in the right. But out of all those, phenylcation is the global minimum, and it can be accessed, although by a few in between connections. It can be accessed from the asymptote I showed, C4H3 plus with acetylene. But the number of isomers, low energy isomers, increases rapidly with the size of the system. So although you can make 6-membered ring, and we ran some ab initio molecular dynamics to find if we can get to that 5 and 6-membered rings, and especially the global minimum, we did, but was not very easily. So some of the ab initio molecular dynamics runs had to run for quite some time to actually access this global minimum. Sometimes they will get stuck in between and not be able to get out of that well, and so on. So phenylcation is possible to make, although as you increase the size of the system with these fragments, things become complicated. So you can have local minimum that is represented, that is formed, but not the global minimum. Of course, global minimum is formed too. So let's go to the next slide. How am I doing in time? So the broad conclusions from this part of the work was that the number of low energy isomers actually increased rapidly with the increasing number of carbon atoms, as you saw last slide, and that the association energies are pretty strong, and association products are internally hot, meaning they can bypass small barriers within, especially if they are submerged. But some transition states can be higher up, and so you can have local minimum. And so global minimum is not always accessed easily by the association fragments, but sometimes they are. So you are able to make cyclic molecules up to 6-membered ring easily in these conditions, sometimes even bigger if you try harder. Let's go to the next slide. So then we thought, well, we can play this game with hydrogen cyanide. I know it's difficult for experimentalists to do that because it's hydrogen cyanide, but we can do the calculations. In fact, our experimental colleagues in Virginia Commonwealth did the experiments, and then they found that they can make pyrimidine ion by simply mixing acetylene ion with hydrogen cyanide in certain conditions, of course, in their experimental setup. And they make this molecule C4H4N2+, which may be as a pyrimidine ion. We looked at the theory behind it. If we go to the next slide, we'll see that the first association of acetylene with HCN creates 17 isomers that span up to like 50 kcals per mole. They are connected in a complicated way. The global minimum has 3 carbons in one end and nitrogen in the other end, and a hydrogen. That's not the right kind of sort of backbone to make pyrimidine, because if you put a HCN with it, it does not make pyrimidine, it makes something else. To make pyrimidine, you need to have a backbone that is carbon-carbon, nitrogen-carbon, rather than a carbon-carbon, carbon-nitrogen. We do have that carbon-carbon, nitrogen-carbon backbone, but that's higher up. That's like the 6th and 7th, or 7th or 8th isomer. So it will have to access these higher energy isomers to make these molecules. If we go to the next slide, then we take the product of the first step, that is the C3H3N+, and then add another acetylene, another HCN to it. And this is the experiment they did, Professor Samuel Scholl's group, and saw that they could make C3H3N plus, they could make C4H4N2 plus, and we had to find out that were robust, that was pretty stable even at higher temperatures. If we go to the next slide, we showed that if you start from C3H3N plus and add an HCN to it, you can make two things: one pyrimidine cation or pyrazine cation. Pyrimidine in which nitrogens are in meta position, and pyrazine in one in which the nitrogens are in para position. And you could make both of either of those two. They both go through submerged barriers. They are not difficult to make, cyclize even, and pyrimidine cation is slightly more stable compared to pyrazine cation. But theoretically, you can make either of these two. So I think pyrimidine cation, making pyrimidine cation is possible in the right kind of conditions, although as you will see later, it's not that easy either. So we'll go from here to the next set of so let's go to the next slide. Now, we looked at small molecules and fragments reacting with each other to make slightly larger molecules. These are traditional radicals or ion radicals reacting with each other. Sometime back, Musa Ahmed's group in Lawrence Berkeley did this experiment where they ionized acetylene in the source, in the gas chamber, and then saw the products. And in another experiment, they let the clusters form by allowing it to flow through the chamber, and then ionize the acetylene clusters in the mass spectrometer, in mass spec. And they saw different types of products. So the top trace is where they see formation of hydrocarbons up to 77. That's phenyl cation probably. But in the second one, where they allowed it to flow and perhaps create clusters and then ionize the cluster, they could see much bigger hydrocarbons produced. So they could see up to 130, 156, 182, and so on. And so we thought that that perhaps this is a way to make. Of course, they definitely said that they could make benzene. So we thought this may be a way to make pyridine as well as pyrimidine. And so we did some theoretical calculations to see if this is a viable way. And if we go to the next slide, we will see. So we did a bunch of calculations where we'll start from this bottom line here. Pure HCN cluster, so number of HCN, so 1, 2, 3, 4, so 2, 3, 4, 5 HCNs, pure clusters. We made the cluster geometry, we got the cluster geometries, then ionized the cluster and saw where that cluster geometry takes us when we allow it to relax in the cationic surface. That's the first one. Then we diluted that HCN by introducing acetylene slowly. So with 2 HCN, we would add 1 acetylene, 2 acetylenes, 3 acetylenes, and so on. And we would run ab initio molecular dynamics within the range of 30 to 90 Kelvin, all the way for like hundreds of dynamics, molecular dynamics calculations, so ab initio molecular dynamics calculations. And then in the third case, we would add 2, 3, and 4 acetylenes with 1 hydrogen cyanide. So these are 3 sets of different different calculations, ab initio runs, and each running up to like 2,000 trajectories. And so I will start with the pure HCN cluster. That's the next slide. The next slide is pure HCN cluster. So we first got the HCN cluster geometries, and that top right corner in that box, you have 3 HCN clusters, and the lowest energy 3-HCN cluster. These are neutral clusters, neutral HCN clusters. So HCN in a linear fashion, then in a cyclic fashion, and so on. And then 4-HCN cluster and 5-HCN clusters. Most of the time when you have multiple of these molecules, the ones that can maximize the number of hydrogen bonding is the global minimum. So that cyclic neutral cluster at the top corner is the global minimum for 5-pentamer of HCN. And once we make these clusters, then we took an electron away and then allowed this that cationic surface to evolve by doing ab initio molecular dynamics calculations. So we would start with each of these different geometries, different cluster geometries, and we'll run tens to hundreds of ab initio molecular dynamics. In the end, what we got is summarized in that AIMD statistics, that bar chart. What we got from pure HCN clusters were growth up to 2 carbon 2 nitrogen species. So C2H2N2, that means 2 HCNs fused with each other. That's pretty much what we got. Other things that we got are neutral clusters kind of geometries where one hydrogen from HCN has been transferred to another HCN. So HCNH plus with CN and so on. So that's the most dominant type of geometries we got in the cationic surface. So we see that no matter what we do with pure HCN clusters, the growth is pretty much sort of capped at pairwise HCN interactions. And in the bottom right corner, these are geometries that are re-optimized after we got that core of ab initio MD run. At the end of the MD run, we'll look at the geometry where we got, and then we'll re-optimize that structure if it looks something interesting and see where it wants to go, if it found a minimum or not. And we did find some minimum sometimes, and those are listed in here. So most of the time you'll see a proton transfer. Only sometimes you will see C2H2N2, as you see in the top two and geometries. So that's basically the pairwise interaction. If we go to the next slide is now showing you the neutral geometries, or the neutral sort of neutral clusters of acetylene and HCN. In the left, you have 2 HCN. Now we're starting to dilute our HCN clusters by introducing acetylene. So 2 HCN with 1 acetylene. We have 3 different geometries. If we did 2 HCN with 3 acetylene and 2 HCN with 1 acetylene, we have a bunch of these geometries. So we got all these neutral geometries, neutral cluster geometries, and then took each one of those cluster geometries and took an electron away, sort of to create the condition of ionization, and then ran the ab initio molecular dynamics. On the right, you have 1 HCN clusters. So 1 HCN with 3 acetylenes here, but we could have I just didn't put the image of the 2 acetylenes and 1 acetylene and 4 acetylenes in here. But these are neutral clusters. So you can see you can form lots of different neutral cluster geometries like this. And these are all bound clusters. Okay, yeah, I'll try to wrap up very quickly. Saw your message, Kyle. So in this neutral cluster geometries, and if we go to the next slide, then if we take the electron away, we see now growth of 4 carbon, 3 carbon and 1 nitrogen, and 6 carbon units, and 5 carbon units. So C5H5N, and that can be pyridyl cation, and as we show in our reoptimized structure on the right. Let's go to the next one, and that is next slide. And this is now where we have a number of acetylene with one hydrogen cyanide, and here also we see growth. We see 4 carbon C4H4 plus. We see C3H3N plus. That's sort of acetylene with 1 HCN. We see still remaining clusters, and we see 5 carbon with the nitrogen. So that's pyridyl radical. We also see benzene. So we can now start to see nitrogen introduction in the cyclic framework. Let's go to the next slide. So we took one of those geometries that looked interesting to make pyridyl cation, and we allowed it to relax. And we see that it does make pyridyl cation with 2 acetylene sort of floating away, and it's strong bond. So it's pyridyl formation is possible. Pyridine ion formation is possible. All right, so with that, I think I'm going to skip the rest of. Let's go to the next slide. Just the conclusion of this. Yeah, let's skip this one. Yeah, so the conclusion of the broad observation of our results is that radical molecular reactions produce small pHs even at low temperature. Iron molecules, of course, can make pH small hydrocarbons up to C6H5 plus, maybe a little bit larger. And neutral cluster, ionization of neutral cluster, of course, also can make pHs as well as nitrogenated pHs. In pure cluster, this is sort of restricted to pairwise interaction. In mixed clusters, you can have larger growth even of carbon framework as well as introduction of nitrogen. And single nitrogen addition to cyclic hydrocarbon is effective, but addition of multiple nitrogens is not that effective. So, so your pyridyl formation is easy compared to pyrimidine formation, pyrimidine ion formation. And with that, I'm going to skip next couple of slides, go to the acknowledgements. I'd just like to give a shout out to the people who I work with. Dr. Tim Lee, who unfortunately, passed away recently. Professor Martin Head-Gordon, Dr. Scott Sanford, Dr. Michel Nuevo, Professor Tamar Stein, and Dr. Xinchuan Huang. And in the left is all the funding places that funds me. Thank you very much. And if you have questions, please.
All right, thank you so much. If you have questions, please do open up that Q&A tab and go ahead and type those in quickly. We don't have a whole lot of time, but we will go over a couple minutes to give an opportunity for a little bit of discussion. In the meantime, I would like to ask, so toward the beginning of the talk, you were discussing the formation of like 6-membered rings followed by additional growth, like I think vinyl acetylene added to something like pyridyl, and you saw that barriers to like forming 2-ring structures were present, so you couldn't quite go there, but maybe there were some other intermediates that were accessible via submerged barriers. I know you're primarily interested in reactions of the form like A plus B goes to C plus D, but at what point do you start considering like the possibility of vibrational relaxation or radiative association to start becoming competitive with dissociation for those larger species?
Well, when it gets bigger, I would say, the smaller ones would probably have to radiate back that energies, the smaller molecules, because it just does not have enough vibrational modes to relax its energy out. So I showed when one of the structures where we had C4H4 plus, actually not the one example you gave, where you could have a sputtering of a proton or a hydrogen that sort of cools the structure down to a molecule that is stable. But if you had larger molecules, then you can perhaps send some of those excess energy into vibrational modes. If you had I don't know where that line is important, where the line is, which is important for vibrational relaxation versus radiative relaxation. Do not have a sort of hunch where that might be. You just have to sort of see case by case. Sometimes these energies are so strong, you just have to relax by quenching, by hitting something rather than or radiating if radiation is possible. Yeah.
Yeah, well, it looks like people are starting to file out because we're past the top of the hour. So I think we'll go ahead and wrap things up here. So thank you again, Dr. Bera, Dr. Palotás, for two very nice talks. I really enjoyed both of those today. Just for those of you who are still here, a quick reminder, as I said at the top, this is our last AstroCheminar for the spring semester. But I do want to remind everyone that we have a very exciting symposium coming up at the fall ACS National Meeting in San Francisco. It's going to celebrate the 10th anniversary of the ACS Astrochemistry Subdivision. So we hope to see many of you there. And again, if you have further feedback for us about these AstroCheminars or other ideas for using virtual platforms to stay connected with the community, even after the pandemic, please do reach out to us. We would really love to hear from you. So on behalf of the rest of the officers, thanks again to our speakers. Thank all of you. I want to thank all of you for attending, and I do hope to see you in San Francisco this fall.
Thank you.